So I spend most of my time thinking about eigenvalue problems, usually with physical context. So it's been a very interesting experience to come to this workshop and see people coming from a variety of different backgrounds. But as I said, most of the time I end up thinking about eigenvalue problems, and what I'd like to tell you today is some thoughts about the eigenvalue problems that come up when you're doing clustering and community detection. So as far as I see it, there's really two ingredients to everything that has the word spectral in it in the realm of clustering or community detection. The first one is you've got to have a subspace, right? Some set of eigenvectors of some matrix, or you can go beyond eigenvectors. You could look, for example, at the factors that come out of a non-negative matrix factorization. But you've got some basis that you're mining for information. And then the second thing you need is a way to extract information about clustering from that basis. So most spectral methods do a pretty good job at detecting large blocks, large clusters in a graph. And they do a pretty good job at detecting things that are disjoint from each other. And what I'd like to do today is explore a couple of ideas of how to extend beyond large disjoint communities from the graph partitioning problem, which is stated purely in terms of the graph, to a constrained integer quadratic program. So we're going to identify the partition with a label vector, plus or minus ones. So plus ones go in one partition, minus ones go in the other partition. And if we write down the graph Laplacian matrix, take this label vector and take a quadratic form with that graph Laplacian matrix, and it gives you a multiple of the number of edges that are cut. So now try to minimize that, subject to the constraint that the vector of all ones, which I'm going to denote by E through the rest of this talk, dotted with your label vector is 0, right? So that's the constraint that the two halves have to have equal size. Right, now this is an NP-hard problem. I haven't actually done anything that moves me away from graph partitioning, but of course there's a relaxation of this to a continuous problem, which is very easy. Namely, instead of saying that your label vector has to be plus or minus ones, you say your label vector is allowed to be real numbers. And instead of reading off things being plus 1 go in one partition, things in minus 1 go in the other partition, I'm going to just use the sign to figure out how to partition things. Right, so this is the basic of spectral partitioning methods. The solution here is the second eigenvector of the graph Laplacian, sometimes called the Fiedler vector. And this is well known, it's classical stuff. Right? So what if you've got a few more clusters? So I want to do 3 or 4 clusters. One thing that I could do is spectral bisection recursively, and that's frequently done in scientific computing. Another thing that I could do is to say, let me treat the first few eigenvectors as giving me latent coordinates, and then I'll do clustering, maybe using k-means. Right? So I've got row 1, row 2, row 3, basically appearing over and over again in the nodes associated with the different clusters. And for the purposes of setting things up on the next slide, I'm going to think about this not in terms of k-means, but in terms of being a matrix factorization. So we've got indicators for the different communities multiplied by a matrix, which in this case would be a 3 by 3 matrix, saying what the direction for each community is. Right? So you can think about this in terms of get latent coordinates and do k-means, or you can think about this in terms of a matrix factorization. The advantage of thinking about this in terms of a matrix factorization is if I start to overlap the communities, it becomes a little bit simpler to think about what to do. So suppose that I talk about a community that's generated with a sort of associative network that Yuri Leskovich was talking about on Tuesday. So I've got probability 1 that things in this group are connected together, probability 2 that things in this group are connected together. Right? So in expectation, essentially what I have is the sum of 2 low-rank matrices. Right? One which tells me the probability of things going up here, one for the probability of things going down there. Right? Now, of course, this is a little bit of a fib because you don't add probabilities, but if the probabilities aren't huge, it's a pretty good approximation. So what I would like to do now is to take this picture and get a factorization that looks roughly like this. Outer product of indicator vectors for the 2 communities of interest wedged with a diagonal matrix with the probabilities, and then the same community indicators again. Right? Now, this is not completely implausible. If I take the sample that I showed you in the previous slide and look at the spectrum, you can clearly see that there's 2 vectors that are special, 2 directions that look essentially like the range of this thing. And if I plot the 2 dominant eigenvectors for this system, you can kind of see that the structure of the underlying communities does appear in the eigenvectors, right? So I've got community 1 over there, community 2 over there, and the overlap region over there. Right? But if I were to tell you with more than 2 communities, please find me the communities in the overlap region, you might be a little bit mystified how to pull that information out of that particular pair of vectors. Right? Really what you would like is a pair of vectors that spans the same space, but looks more like indicators. Right? And this is, in fact, a pair of vectors that spans the same space as those eigenvectors. Right? So how do we get a basis that looks like this rather than an eigenvector basis that looks like that? So there's a simple trick, which is we're going to say I want something that's sparse and non-negative, right? And that's all I'll use. I'll say that characterizes what I think of as an indicator vector well enough. Let's skip the 0, 1 part. So now let me write down a linear program that tries to pull out things that are sparse and non-negative, right? So actually the L1 norm in this case is just going to be the sum of the elements. I want something that's in my space, so it can be written as my original basis times some y. I need to specify that I don't want the 0 vector. So let me say that some particular seed is non-zero. So I want to have some particular node or nodes in the community that I'm going to pull out. And then I want component-wise non-negativity, right? So, and given that, it works almost like magic, right? And in fact, you can show that if your matrix U were exactly equal to some scrambled up version of a set of indicator vectors for communities that you were interested in, and each of those communities contained at least one element that was in no other community, then when you do this linear program, you're always going to pull out the indicator vector for the smallest community containing your seed node. If there's 2 communities of the same size, you may pull out a linear combination of those indicator vectors, but that's sort of a degenerate case, right? Now, of course, in truth, you never actually get this. There's some noise. You need to do thresholding. I'm not going to go into that today, partly because I don't have a very good story about it. Right? So this seems like a pretty cool method. I was very pleased with it. Right? But then I started looking at some situations where I was actually interested in overlapping communities. And in many cases, I was interested in lots and lots and lots of very small overlapping communities. And if I was going to try to do something with eigenvectors, and I've got 10,000 tiny communities that I want to find, I don't want to compute 10,000 eigenvectors. Right? It's going to take me a long time. It's going to take a lot of storage, and it's kind of boring. Right? So really, the method here is OK, but the space I want is something that's maybe not the space of eigenvectors. Right? So what do I want? Well, let's consider why eigenvectors are a useful space to probe in the first place, and then think if we can find another space that has similar properties that will do as well. Right? So one reason why eigenvectors give you useful information about communities or clusters or however you want to think about it is the reason that we talked about at the very beginning when we were looking at classical spectral partitioning. Right? Namely, you can write down quadratic forms involving the graph Laplacian, the adjacency matrix, maybe the diagonal matrix with degrees on the diagonal, maybe Newman's modularity matrix. And if you put indicator vectors into that quadratic form, what you get out is properties of the indicated subgraph. Right? So if I look at S transpose AS, I get the number of edges within the subgraph. If I look at S transpose DS, I look at the number of edges incident on the subgraph. Right? Take the difference of those two things. That's the same as S transpose LS. That's the number of edges cut. Right? S transpose BS, where B is Newman's modularity matrix, gives me the number of quote-unquote surprising internal edges. Now, this on its own is okay. What's also interesting, though, is that you can take ratios of these things in order to get normalized measures of interesting properties about subgraphs. Right? So for example, if I look at S transpose AS over S transpose S, that's the number of edges in an induced subgraph divided by the number of nodes. So this is the mean internal degree inside of some subgraph. Right? S transpose LS divided by S transpose S is number of edges cut relative to the size of your set. Right? You can look at fraction of incident edges that are internal. You can look at fraction of incident edges that are cut. You can look at the mean number of surprising internal degrees of freedom in a subgraph, whatever you want. Right? So looking at ratios of these quadratic forms gives you some normalized measure of something interesting about a subgraph. And of course, the interesting thing for me about ratios of quadratic forms is ratios of quadratic forms immediately give you eigenvalue problems. Right? So if I've got any symmetric matrix K and any symmetric positive definite matrix M, and I look at minimizing or maximizing, or in general finding a stationary point of this Rayleigh quotient, right, this ratio of quadratic forms, that's equivalent to finding an eigenvalue, an eigenvector. Right? So the stationary vector is your eigenvector, the stationary value is your eigenvalue. So when I say eigenvalue and eigenvector for the purposes of this talk, I may be talking about a regular eigenvalue problem or a generalized eigenvalue problem. They're 6 of one, half a dozen of the other. Right? Now the cool thing about this is something that's easy to solve despite the fact that it's a non-convex optimization problem. In fact, it's basically the only non-convex optimization problem that I know how to solve easily. And so it's a lucky thing that it comes up as often as it does. Right? So, of course, this is something that if I do this optimization, I'm optimizing over real vectors in general. Right? But I'm interested in indicators for subgraphs. So what can I say? Well, if I take any old vector, right, let's normalize it so X transpose MX is 1, then I can write it as a linear combination of eigenvectors. Right? So W is going to be my eigenvector basis here. And X transpose KX is going to be a linear combination of the eigenvalues with related weights. Right? So ZJs are the weights in my combination of eigenvectors. The ZJ squares are going to be the weights in my combination of eigenvalues. Right? So my Rayleigh quotient is actually a weighted average of the eigenvalues of my pair. And if I take that weighted average and I get anywhere close to the maximum or the minimum, well, I can't take a weighted average of a set of things, have it come out close to the maximum, and know that most of the weight is far away from the maximum. Right? So if the weighted average is close to some extreme value that's a bound on what it could possibly be, then you know that in the space of eigenvectors that's associated with the eigenvalues close to that bound, you have to have some reasonably good approximation for the indicator vector for the set that you're interested in. Right? And so this justifies, or this is one justification for looking at invariant subspaces associated with extreme eigenvalues in order to try to find interesting subgraphs. Right? Let me turn around and look at a completely different reason why you might think about eigenvalues and eigenvectors as giving you useful information about subgraphs. And this is related not to optimization, but to dynamics of diffusion processes, right? And I want to start off thinking not about a graph, but about 3 tanks of water, right? So I've got 3 tanks of water, maybe 3 coffee cups if you like, and they're connected by thin straws, right? And at some time, I go and dump creamer into one of these coffee cups. I walk away, and 10 minutes later, I come back. Or maybe not 10 minutes. Maybe 30 seconds later, I come back. And I've forgotten where I dumped the creamer in, right? Well, what am I going to be able to say? I probably won't be able to say that I dumped it into that corner of that coffee cup, right? Because it's mixed up by this point. But I can say I dumped it into that coffee cup because I look and there's a lot more creamer there than there is in either of the other 2. Right? If I went away for an hour and came back, then everything is homogenized and I can't tell anything. Right? So in some sense, the fact that this is a unit is reflected in the rate at which you forget information about how stuff went into there. Right? Okay, so that's a physical picture. Let me give you an analogous social picture. Let's suppose that I came up with a joke, right? It happens from time to time. Fortunately, not too often. So I come up with a joke which I think is funny, right? That's day 1. Day 2, everyone in my family knows this joke, and maybe by day 3, my mom has told someone else, right? So you can plot out who is in my family by who knows this joke after a certain period of time, right? That's thinking about things diffusing forward. You can think about things the other way around, too, which I often like to do, which is to look at how quickly the source is forgotten. Right? So day 1, I came up with a funny joke. Day 2, you know that somebody in Cornell CS came up with this joke. Day 3, you know that somebody who posted it on a website somewhere knew about this joke. Right? Actually, this is probably day greater than 3, but the point remains. Right? So whether you walk forward or backward, you've got information about community structure, whether it's the CS department or my family, embedded in how things spread out, how things diffuse within a graph. Right? Okay, so I can look at this in terms of matrices. I take my transition matrix for a random walk, right? Since I'm a numerical linear algebra guy, I work with column vectors, so I've got D inverse over there rather than on the other side. Alpha is some self-transition probability. I set it equal to 0 when I'm allowed to, otherwise call it a half. Right? So I start at some initial distribution, which is concentrated at a particular node. I take k steps. My distribution is s to the k times p naught. Right? And as time goes to infinity, that's going to a stationary distribution, which is associated with whatever the degrees in the graph are. Right? But it may take a while to get there. Right? If I look at things the other way around, S transpose to the k times q naught, where q naught is the distribution, q naught is my initial distribution, sorry, gives me the conditional distribution on where I started given a uniform prior. Right? And that thing is going to a constant vector as time goes to infinity, right? So given a uniform prior, if I run things for a long time and say, where did this start, you have no idea, right? So if the graph is undirected, these two S transposes similar to S. This is usually what I think about. S transpose and S are the same thing if the graph is also regular. Right? Okay, and so there's a theory for when you've got loosely coupled Markov chains. So think of my family talking within itself a lot, but not necessarily talking to everybody else, right? And that says that, according to Simon-Ando theory, when you look at mixing in these chains, you've got 2 phases. The first phase is everything mixes pretty rapidly locally, right? That's when I dump creamer into my coffee cup, run away, and a few seconds later, the creamer is all through the coffee in that one cup, right? The second phase, you've got gradual equilibration between these loosely coupled Markov chains, right? So a little bit of creamer leaks into the other cups, it gets pretty quickly uniformly distributed. So after a short period of time, I can write down the distribution of Creamer approximately as there's this distribution in this cup, this in this cup, and this in this cup, and there's no interesting internal variations. Right? So I can look at that pattern of mixing and think of that as a way of getting out what local structure exists in my network. Okay, so in terms of eigenvalues and eigenvectors, if I've got a bunch of exactly decoupled Markov chains, then I've got an eigenvalue of 1 with multiplicity c, where c is the number of chains. There's a large spectral gap, assuming that I've got rapid mixing. The eigenvectors of S tell me what the local equilibria in each chain are, and the eigenvectors of S transpose give me indicators for which nodes are in the chains. Right? If I weakly couple things, I've got almost the same sort of information. So I've got a cluster of eigenvalues close to 1. I've still got a large gap between the cth and the c plus first eigenvalue. But now my eigenvectors of S are local combinations of these local equilibrium vectors. And my eigenvectors of S transpose are linear combinations of the indicators. Right? So if I look at the first few eigenvectors of S transpose, they're going to be roughly constant on each of my sets. But I don't necessarily know what the constants are. Right? Okay, so now I've got two different reasons why I might be interested in looking at eigenvectors. But you know, if I compute, I'm actually doing something to get eigenvectors. And that something is actually connected both to optimization of quadratic forms and to the asymptotic dynamics of random walks. Right? So remember this variational characterization of eigenpairs. So I can write down that an eigenvalue and eigenvector correspond to a stationary point and a stationary value for a Rayleigh quotient. Right? Now suppose that I've got some subspace that I want to explore for approximate eigenvectors. The usual way to do this is the Rayleigh-Ritz method. I say V is a basis for my subspace. I say some linear combination of the elements of that basis. I get a vector x, and I want this constrained optimization problem to be satisfied now. So I'm going to look for a stationary point of this projected Rayleigh quotient, and that gives me a projected eigenvalue problem. Right? The eigenvalues of this are proxies for the eigenvalues of my larger systems. The eigenvectors are approximations for the eigenvectors, assuming that V is a rich enough space. Right? So how do you build up a rich enough space? Well, in numerical linear algebra, we're used to only being able to do matrix vector multiplications. If all you're allowed to do is matrix vector multiplications, then what you do is matrix vector multiplications, right? So we start with some vector, and we keep multiplying over and over again, which you may recognize as exactly the same thing you do if you trace the trajectory of a Markov chain, right? You start with some vector, and you multiply by the transition matrix over and over again, right? So how do Lanczos methods work? In essence, what you do is you generate a basis for a Krylov subspace, and you use Rayleigh-Ritz on that subspace basis, and then you restart if the subspace gets too big. Right? There's a little bit more to it than that, but that's the big picture. Right? But now what happens if you don't go all the way to convergence? Right? So what happens if I think about looking at these Ritz vectors and Ritz values? Right? So I've gone out a little distance. I've now got a Krylov subspace. If I started at a single point, this Krylov subspace may correspond to a few steps of diffusion out from that point. It's not explored the entire graph yet. It's not giving me global information. Right? But if I'm interested in local communities, that's a good thing. Right? But what is it giving me? Well, the Ritz values are defined by an optimization, so I know I'm getting something that's maximizing or minimizing this Rayleigh quotient over this space that I've explored. I can also think about it in terms of dynamics as follows. If I look at an eigendecomposition of, say, some transition matrix where I've got a set of eigenvectors Vj and corresponding eigenvalues lambda j, I can write down my initial vector p naught as some linear combination of the eigenvectors, and I can tell what's going to happen in successive steps because the coefficients in that linear combination are going to be multiplied by powers of the eigenvalues. Right? So eigenvalues that are close to 0 correspond to things that I forget about almost immediately. Eigenvalues close to 1 are features that persist for a long period of time. If I do a Krylov subspace approximation and then do Rayleigh-Ritz on top of that, I can do something very similar with Ritz values and Ritz vectors. Right? So I've again got something where I can write down my initial distribution as a linear combination of Ritz vectors. And for R steps, where R is the size of the Krylov subspace I used, I get this same picture of the dynamics, right? That I can write down what's happening in terms of multiplying the elements or multiplying the coefficients in this linear combination by powers of the Ritz value, right? So where eigenvalues give you something about the long-term dynamics of a Markov chain, these Rayleigh-Ritz approximations, given a Krylov subspace, tell you something about short-term dynamics, right? Intermediate asymptotics, which is the type of thing that I like to think about. Okay, so what's the idea here then? The idea is let's use unconverged subspace computations in order to try to get local structure, the same way that we use eigenvalues and eigenvectors in order to try to probe the global structure of a matrix, right? So what's the analysis? So invariant subspaces, well, the dominant eigenvectors tell me something about the dynamics of long random walks. This tells me something about the intermediate dynamics of shorter random walks, right? Invariant subspaces, taking a few eigenvectors is good for global information. This is much more local, right? Computing eigenvectors, particularly if I need a lot of them, that's expensive. This is cheap. Maybe for eigenvectors, I need a large space in order to resolve very fine features. Here, maybe a small space is OK. Right? So my current favorite method, which is completely ad hoc and which I'm much less happy about than all of the mathematics that just came before this, is to pick a few seed nodes, do this Rayleigh-Ritz approximation to get some subspaces, and use the linear programming that I told you about before in order to try to extract indicator vectors from that subspace. So rather than prove anything, because I've proved very little about this method, let me show you how it works in a few examples. So unfortunately, these are all tiny. Mostly this is because most of the community detection literature ends up dealing with tiny graphs. So for simple graphs, you pick out things out pretty easily. Squares here correspond to the nodes that were detected to be in a community after thresholding. The color is associated with the raw score vector. This is a case where you can see very clearly from looking at the spectrum of the transition matrix or normalized adjacency matrix that there really ought to be 4 clusters. This looks like it ought to be an easy case, right? And in fact, here the Ritz values that we used were pretty much the same as the eigenvalues. Everything converged by the time that we were looking at it. Zachary karate graph, it works. There's not a whole lot more interesting to say about it. Spectrally, though, it's a little bit more interesting. And this, in fact, comes out because if you poke at this a little bit more, you can do things like find out that this piece will split off if you let it. This is who played who in football games. Again, things work out pretty well. The spectrum is a little bit more interesting. It would be a little bit harder to guess how many groups there were from looking for gaps in the spectrum here. The dolphin graph is not so interesting. Let's look at a couple of synthetic benchmarks. So Lancesetti and Fortunato have published a graph generator that gives you power law degree distribution graphs that you can use for testing community detection networks, which I kind of like. It's got a mixing parameter that essentially says how many connections you have outside versus inside. So larger mixing makes things worse. This is a case where I've got non-overlapping communities. There's a clear gap in the spectrum. Things work out pretty well, so you could pull out one of the communities just by looking at this score vector if you threshold properly. This, though, by the way, was pulled out by taking 10 steps of a random walk and using 3 Ritz vectors, right? Where the number of communities here is, I've forgotten, but much larger than 3, right? So you certainly don't need number of communities vectors to pull out this structure. From u equals 6, it's about the same. There's no nice spectral gap, but again, you can pull things out. It's a little bit noisier this time. What about when we've got overlapping communities? Here the spectrum is much more funky. You've got kind of a bend in the spectrum at the right place, but not a whole lot more than that. If you just do the raw method that I discussed with a single seed, you don't get a whole lot. If you combine information from two seeds, you actually do a pretty good job of reconstructing what one of the communities is. Okay, so enough of me hand-waving. What's the big picture here? The big picture here is spectral methods are nice, right? They've got sort of this nice intuition. They've been around for a long time. But there's two things that I don't like about them. One is that most people just use them for partitioning. And I hope I've convinced you today you can go a little bit beyond that by thinking of different ways to mine the eigenvectors for information. And the other thing is, if you're interested in local communities, you might need a lot of eigenvectors in order to resolve it, but there's alternatives to looking at eigenvectors that are cheaper to compute and may give you better local information. The algorithm that I described is still a long jump from what I'm able to theoretically justify. The thresholding algorithm I have works sometimes and fails embarrassingly at other times. And I was very excited to see Yuri Leskovich's pointers to data where there's actually ground truth. So I'm planning on going back and testing on some of that as soon as I get back to Ithaca. Thank you.